Okay, so, well, Dr. Porter is a visiting assistant professor of environmental science at Wittenberg University in Ohio, which is a fairly new position, but she's also a researcher associated with the ice core paleoclimatology group at the Bird Polar and Climate Research Center at The Ohio State University, where she's been working for a bit longer. And her research really extracts information from ice cores in order to understand past climate and ocean conditions. And these are, of course, crucial to modeling, to building models that can best represent future interactions between atmosphere and climate and ocean circulation. And so her work is really interesting, I think, and really exciting and incredibly relevant to today's challenges with understanding how the climate's likely to change, how it's changed in the past, and what the key players are in that cycle. So I'm happy to welcome Dr. Porter today, and with that, I'll turn it over to her.
All right, thank you so much. All right, so hopefully you all can see this. So the title of my talk is a little general. Time after time, you got to put a pun in there, but contextualizing recent climatic changes using natural archives of Earth's climate history. So what I thought I'd do is really give sort of a background on the knowledge of what we have in climate science today, moving through towards sort of the fundamentals of using ice cores to reconstruct Earth's history, and then what I do specifically with the ice core group. I'm kind of the atmospheric scientist of the group. So I'll go into my research near the end there. So just to give a little history of me and what I do, although thank you, Shannon, for the intro. So I'm currently at Wittenberg University in a primarily teaching position, but my research is based in what I was doing at Ohio State. So I did my PhD there and my postdoc there. And so I still very much have a connection with the Bird Polar and Climate Research Center. And as I go through talking about ice core stuff and I say, oh, we have this and we have that, I'm talking about the lab at Ohio State. So just to clarify that. But anyway, I was born and raised in Knoxville, Tennessee. I'm kind of a country girl at heart. I did my bachelor's at the University of North Carolina in Asheville, and then I did my master's at the University of Alaska in Fairbanks. And it was there that I really fell in love with the Arctic and ice, and I wanted to study it more. And ironically, to do that, I had to move to Ohio, and that's where I could really study the ice. And that's when I started working with the ice core group. So I like to say I wear a lot of hats in my job. And so depending on who I'm talking to, I might change what my job title is. I might say I'm an ice core paleoclimatologist trying to reconstruct climate history from ice cores. I might just say I'm a climate scientist because I do focus on what's happening today as well, not only the deep past. And then my background is really in atmospheric sciences. So my degrees are in atmospheric sciences. And I'm the atmospheric scientist of the group. So I look at sort of the large scale atmospheric dynamics and how those get recorded in the ice cores. But one of the things you'll see in when I'm talking about ice cores is it really takes a village to understand these cores. So we have people from all different sorts of backgrounds that are looking at these. And so my fascination with not just ice, but with the climate and the atmosphere really started as a kid. I loved the weather. I was a big weather geek, always tuned to the Weather Channel. But today I focus on the ice and its many forms. So I thought I'd do just a background. I know this is probably gonna ease you in too slowly. I'm sure all of you are familiar with what's happening in the climate these days, but we all know that the climate is warming. We can see that if we look at our global temperatures rising at rapid rates. So going back through our observational record to 1880 up to today, you can see that warming trend. And just a side note, if you were born after February 1985, you've never experienced a cooler than average month on this planet, which is really eye-opening. to me anyway. And we know too from the Intergovernmental Panel on Climate Change, the IPCC, they just had their most recent report come out this past August, the 6th assessment report. And to quote them, it is unequivocal that human influence has warmed the atmosphere, the ocean, and land, and widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. And so if you don't trust the IPCC, here are some numbers for maybe why you should. It's a team of over 200 authors from all around the world. There are 14,000 scientific publications that are assessed that go into this report, and 78,000 different review comments through the different rounds of review that it has to go through, and even has to be accepted by different governments. So this is really the go-to source if you're interested in climate science, the IPCC there. So some of the effects we know from this warming are the increase in extreme events. If you turn on the news, you will not be able to avoid some of these events that are going on recently. So whether it's extreme heat that we've seen in parts of the Western US, the wildfires that have been raging there as well. This recent hurricane season was really extreme as well. So there's a picture there on the bottom of some of the extreme flooding that took place from the remnants of Hurricane Ida as it moved up through New York and the Northeast. Of course, our Arctic sea ice loss. You can't do a climate change talk without a polar bear. So extreme loss in the Arctic sea ice, and then sea level rise as well. So this is a picture from the Ile de Jean Charles in Louisiana, where I think over 98% of the land from the small isle is now underwater. So lots of extreme events occurring from this warming that we've been seeing. So they are becoming more common. If we just look at 2021, not quite up to date, but January to September 2021, we experienced 18 events in this country that each cost at least over $1 billion. And these events, like I said, are increasing as we go through time, and we can know that based on just the average number of events that we typically get in a year that would cost over $1 billion. The average is about 7. So already this year we're up to 18. Last year, 2020, was a record-breaking year. We saw 22 events that each cost over $1 billion in the US. So if we add up kind of the total of some of these extreme events, just since 1980, they've exceeded $1.875 trillion. So, whenever you hear anyone say, can we afford to try to do anything about climate change, I would argue, can we afford not to? Because that is a big price tag that comes with that. Even in Ohio, where I know you all are not, but this is where I am. And so I've got some personal experience here. In June of 2012, we had a derecho move through. So this band of storms and really strong winds that moved through at the end of June, knocked out power for days in our region. And then right after that, we moved into a heat wave. So with temperatures and heat indices well over 100 degrees and many people without power, caused a lot of issues in the Columbus area. In more recent times, in 2019, we had some tornadoes move through the Dayton area. So you can see on the map there, all the little kind of red markers are where tornadoes actually drop down. And I will say, I mentioned that as a kid, I loved the weather, and I was really, really fascinated with tornadoes especially. But in that fascination also came quite a lot of terror. And so I wear a Fitbit. I've got my heart rate monitored. And when these storms moved through, this is a little graph here of what my heart rate did. So you can tell when we went under a tornado warning here in Columbus, even though no tornado actually dropped down, it still caused quite a bit of stress for me there. but so that just kind of goes into the fact that there's a physical toll here with the damage associated with these events. There's a financial toll, obviously, with the damage that goes through, but there's an emotional toll as well that we should consider as these events increase. And so not only do we have these extreme events tied to this warming, another more evidence that we know that the Earth is warming is from the disappearance of ice on the planet. So we know that the ice is disappearing. We can see that with pictures from around the world. This is the Furtwängler Glacier. It's a glacier on the summit of Kilimanjaro. And you can see the pictures here from 1999 to 2012, how that glacier has shrunk not only kind of in the horizontal, but also in the vertical as well. And so if you look here at on the right, this is the aerial extent of the ice in 1912, which is in sort of the gray color, and then in 2013, which is the green color. And I always like this image because the 1912, it kind of looks like a hand reaching up. But this glacier here in the middle, this is the Furtwängler Glacier. And I believe, and I might be wrong here, but I think this glacier is gone now. If not completely gone, very close to. But there are still some ice in the northern ice fields, but essentially over 90% of the ice has disappeared since 1912. So within, I would say, a few decades, we probably will not have ice on Kilimanjaro. Another glacier that is in distress, we'll say, is from Puncak Jaya. This is in Indonesia, on the island of Papua. And so this is an image of the glacier from 2012, and I've got a little time lapse here. So you'll see it kind of going through the years 2016 to 2018. And so you can see how much this glacier has disappeared, even in worse shape today. And again, within a few years, there will likely not be ice here in Indonesia. In southern Peru, this is up in the Andes. This is the Quelccaya ice cap. This is a place that's near and dear to my heart. I did go on a field expedition here, only once, unfortunately, but fingers crossed, maybe sometime again. But what you can see on the left is the margin of the ice in 1977. And from that same vantage point on the right, you can see it here in 2002. So you can see how far back the ice has retreated just in those couple of decades. So this is another area of the Quelccaya ice cap in 1978, and you can see circled here is this boulder. So that's going to be our reference point for when we show the next picture here. But we're going to kind of move a little over to the right. We're going to change perspective when I show the next picture. But again, you'll see how far back the ice has retreated. So this was 1978. And then here we go in 2018. So we've moved over. Here's the boulder. But again, you can see how far back the ice has retreated. There are these large melt ponds all around the ice cap as well. And then there are big drop-offs down into a valley that really puts this place in a precarious location because, this lake is very unstable. So any kind of large boulder or piece of ice falling into that lake, small earthquake, that water could breach and easily run down the valley, causing a glacial lake outburst flood. And these are forming all around this region. This is the Contextualizing glacier. It's also part of Quelccaya. And you can see it here in 1978, beautiful, robust glacier. And then 2018, you can see how far back it's retreated. Another huge melt pond has developed. And again, these pictures don't do these ponds justice. They are huge. I think this one is over 200 feet deep, estimated. So a lot of water just sitting there precariously. Another picture here from Peru, not quite in Quelccaya, but in the Colla area where they have a festival to kind of celebrate the glacier. And they used to take pieces of the glacier and use that water for medicinal purposes. But In recent festivals, they have not been doing that because the glacier has been retreating so much. So you can see here a picture in the 1930s compared to one in 2006, and kind of tried to overlay them here. So you can see again how the glacier has receded in these areas. So I always like talking about the ice disappearing because there's a lovely quote by Henry Pollock, and I'll just paraphrase, but essentially ice has no agenda. It doesn't have political baggage or anything like that. So it just, when it gets warm, it melts. So when you see these huge chunks of ice melting, it tells you it's getting warmer. So we know that we have a lot of changes going on right now. But how do we know that those changes are unusual? Because our observational records only go back about 150 or 200 years, and Earth is 4.5 billion years old. So we only have this tiny snapshot of what's actually occurred on this planet. Fortunately, Earth keeps its own climate records. And it does this through various natural archives like tree rings, corals, ocean and lake sediments, speleothems, pollen records, and then the one I'm going to focus on today, ice cores. So through all these natural archives, we can get an idea of what Earth's climate history was back well before we had these observational records. Okay, so what is an ice core? I'm sure many of you are probably somewhat familiar with ice coring, but if not, I'll give you a little background here. So I'm showing a picture again of the Quelccaya ice cap, and this is the margin. And what you might notice about this picture are these really beautiful layers in the ice, very distinct layers. And this region has kind of a monsoon climate, so a very distinct wet season and dry season. And so during the wet season, they get their snowfall. And then when it's dry, you get dirt and clay and sand kind of kicked up from surrounding areas. And that creates kind of a thin, dark layer. And then the next year, you get more snowfall. So these are annual layers going back in time. And they just accumulate as you go up. So what we do is we simply drill down into these ice caps with a drill you can see here. Pull up about 1 meter at a time, and you just keep going down the same hole, collecting another meter until you hit bedrock. And you can see this is what the core looks like coming out of the drill. But essentially, once we do that, once we get to bedrock, we've got a record of all of those layers. And the properties of that ice can tell us about the climate at the time that that layer was deposited. So we have ice cores at Ohio State there from all around the world. So you can see here, places you would expect like Greenland, Antarctica, obviously a lot of ice there, but other places like what we call the third pole, which is the Tibetan Plateau. That's the third largest repository of ice on the planet. Also in the tropics, in the Andes of Peru and Bolivia, on Kilimanjaro at Quelccaya, we have ice from there as well. And so Ohio State has the largest collection of tropical ice cores than anywhere in the world. So to analyze the ice, this is one of our cutting rooms. So you can see the bandsaw there, and one of our researchers, Emily, running the samples, the ice samples through that bandsaw to cut it down into little cubes. But essentially, this is what a cross section of the core looks like here on the right. So half of it we save as an archive, put that into the freezers. That's for future generations to study. It'll hopefully be there in the long run, especially places where there won't be ice for much longer. Places like Kilimanjaro or Quelccaya in Indonesia, that ice will be in Columbus, Ohio, for future generations to study. But the other half of the core, we have to cut down into samples to study the chemistry of the ice, the anions and the cations, to study the dust content, to study the isotopic content, so the isotopes of oxygen and hydrogen as well, and then some of the radioactivity of the ice as well. So that's kind of a generic cross section. each core will be different depending on, what other samples are being taken as well. And so those little cubes that Emily's cutting in the cold room will eventually go to the class 100 clean room at Bird Polar. And you can see all of those little cups there on the right filled with ice samples, and those go through all of the instrumentation that we have in our clean room, like the Coulter counter to measure the dust content, like the ion chromatograph to do the chemistry. We also have an SP2 to do black carbon. So we're focusing on looking at wildfire histories in some of our cores from those black carbon residue that's in the core. So ice cores can tell us a wealth of information. So we can understand things like temperature based on the isotopic content. We can understand changes in the atmospheric chemistry, your sulfates, your nitrates, things like that. We can look at the net accumulation, how much snow fell in that region. You can do that just based on the thickness of those layers. We can look at the dust content, as I mentioned before, whether you're getting more dust picked up in the wind from, various sources. Vegetation changes. If you find pollen in your cores, you can understand what type of vegetation was growing at that time. Volcanic histories. If it's a local volcano, sometimes you'll get a thick layer of ash. If it's a very distant volcano, you might get a peak in sulfate because volcanoes can emit a lot of sulfate. Anthropogenic emissions. So the air bubbles trapped in the ice kind of give us little vaults of previous atmospheres. And so you can measure the content of carbon dioxide in that ice, or the methane levels in those little air bubbles to see what the past concentrations of those emissions were like. And then entrapped microorganisms. Those could be, little insects that we find in the ice, or things like bacteria and viruses in the ice. So there's a postdoc at Bird Polar currently working on looking at viruses and bacteria in some of the ice from the Tibetan Plateau. So I mentioned the stable oxygen isotopes. So we look for oxygen 18 and that ratio to the typical oxygen 16. And we use that as a proxy for temperature. So you can see the graph on the right here going back 25,000 years. And this is ice cores from all around the world. Again, South America, Greenland, Tibetan Plateau in China, Antarctica as well. And so you can see those histories of temperature, where the Holocene, the last 10,000 years, relatively stable. You can see the Younger Dryas around 12,000 years ago, and then going back into the last glacial stage. And then the oldest ice core that was ever obtained was not by our group, but it's a core from Antarctica, Dome Sea. And so you can see that here on the top in black, going back 800,000 years. And then you can see that's compared with a marine core as well. So reproducibility in those records, really nice. And the similarities there kind of add validity to them as well. And you can see those glacial and interglacial stages every 100,000 years or so, going back almost 1 million years. So another thing we can look at is the chemistry of the ice. So this is a graph here on the right from Quelccaya in southern Peru. So we're looking at fluoride, chloride, and then the accumulation. And I've got highlighted here these two peaks in chloride and fluoride, one around 1350 and one around 1800. And these coincide with periods of low accumulation. And so we've looked too at the historical records from this region, and this tells us that these were associated with drought events, pretty major droughts. And so why we get these peaks in fluoride and chloride, chloride comes from these salt flats that are around this region, so sodium chloride. And so there's a picture here which shows the salt flat when it has a layer of water on top from the precipitation. Really nice image, kind of a beautiful reflection, looks very Instagram worthy. But if there's not much precipitation, if it's really dry and you're in a drought, this is what those salt flats look like. So very easily that salt can get kicked up into the wind and deposited up in those mountains closer to where our drill site is. And so that's why we get those big peaks in chloride during those drought events from these surrounding salt flats. We can also look. Hi there. I don't know if I dropped or what happened.
I think we must have dropped it here. I'm sorry. It looks
Oh,
like
no.
it's back in. So apologize to everyone. That was not Dr. Porter's fault.
Okay, let's see if I can. Okay, can everyone see that?
Yes.
Okay, all right, thank you. All right, so not only can we see those drought events in those sodium and chloride records, we can also look at pollution, so sulfate and nitrate pollution from human activity. So this is a core from the Greenland summit going back to 1750. So you can see sulfate in blue, and you see these big peaks associated with volcanic events. But also after 1900, you can see this really big increase in sulfate. That was mainly due to the burning of coal, really high sulfur content coal. But then sulfate starts to go back down around the 1970s. And that was due to the passage of the Clean Air Act and similar legislation in Europe as well. In red, you can see nitrate levels. So again, nitrate going up really after about 1950 or so. Nitrate typically comes from things like car emissions, but also agriculture is a big contributor to nitrate. So we can see here too another core from West Central Greenland that our group drilled. And this is looking at two volcanic events. One was in 1809. We don't know where it came from, but it shows up in a lot of different cores. But it's this peak right before the big Tambora eruption, which is well documented in many different paleo archives. But this was in 1815, and it takes about a year or so to kind of distribute around the globe and work its way up to Greenland. So we call that peak about 1816. But Tambora had a big effect on global temperatures, caused the year without a summer, which was in 1816, which really influenced the arts at that time. So this is a painting by William Turner called Lancaster Sands. You can see these beautiful reds and golds and oranges that he was painting in these sunsets. And that was caused by, the high amounts of sulfate in the atmosphere from this huge volcanic eruption. We got things too, like Mary Shelley's Frankenstein. She was vacationing in Switzerland, and it was too cold and rainy to go outside and enjoy it. So they all stayed in and decided to write ghost stories. And that's how we got Mary Shelley's Frankenstein. Happened during the year without a summer because of Mount Tambora. So going off on a little tangent there, but we can also look at our dust records in ice cores. And this graph is a little bit heinous, I will admit, but what I want you to focus on is shaded in gray about 4,200 years ago. And if you look at that circle, this is looking at dust content from the northern ice field in Kilimanjaro. So we get this really huge dust peak around 4,200 years ago. And if you actually look at the core, it's, a really thick layer of just dark dust. And this was associated with a major drought event that occurred in this region. It's actually written about on tombs from ancient Egypt. So this is a translation of one of the hieroglyphs from the tomb of Enkhtifi that says the whole of Upper Egypt died of hunger, and each individual had reached such a state of hunger that he ate his own children. So being able, obviously that's a horrible time to live through. I don't want to downplay that at all, but for us to be able to connect what we actually see in the core with these written historical records is really unique and really awe-inspiring, in my opinion. So the last thing too that we can get from our ice cores focuses on the air bubbles. So those ancient atmospheres trapped in these little bubbles. And we don't do this in the lab at Ohio State, but we'll send our samples away to other labs to get this content. But again, you can see here those little air bubbles trapped. And so we can measure the composition of carbon dioxide and methane in those little bubbles to see what those past atmospheres were like. And that gives us that context to see how these changes today are unusual. So I'm sure you're all familiar with the Keeling curve of carbon dioxide levels. This is what we've observed just in the past 70 years or so. Going back to 1958, our current level is about 414 parts per million of CO2. But is this just part of, big cycles in the atmosphere? We only have this tiny snapshot. So let's extend it back with our ice core data. So we can go back to 1700, and you can see that that's starting to look a little unusual what we're seeing today. Let's go back 10,000 years. And now it's starting to look really unusual. 10,000 years ago, we've got pretty steady levels around 280, 270 parts per million. And then today, well over 400. Let's go back to that oldest ice core ever obtained 800,000 years ago. And you can see, again, how unusual what we're seeing today is. You do see big swings in carbon dioxide, but it never gets above 300 parts per million. And today, again, well over 400. So you need this longer context of Earth's climate history to understand how unusual the changes are today. So with that, I thought I'd just kind of switch gears just a little bit and talk about some of my work specifically. So I mentioned before, I'm kind of the atmospheric dynamicist of the group. So I focus on these large scale circulation patterns and how those get recorded in the ice. And so one of the current projects I'm on is looking at Pacific decadal variability over really long time scales over the last millennium. But if you think this started, what got us inspired for this was this big El Nino in the 2015-2016 year. So this made the headlines as, a monster climatic event, a monster El Nino could bring relief from misery to California. California was in the midst of this really terrible drought. I know it's gotten bad again, but there was hope that this monster El Nino would bring rains to Southern California. You can see here what the impacts of an El Nino look like on the US. So it's typically wetter along Southern California and the Southern US during El Nino events. But if we look at what actually happened in that year, it did not bring the relief that was hoped for. So you can see the headlines on the right here. El Nino falls short, not enough to quench the drought. And if we look at the rainfall anomalies for other really strong El Nino events, we had a strong one in 1982 and 1983, a strong one in 97, 98. And those purples and blues that you see over Southern California mean they had almost twice the amount of their typical rainfall in a year. But in 2015, 2016, it was still rather dry. And so it kind of got us thinking of, okay, well, what if this is driven by sort of this long-term variability? So we know in the Pacific, you have these sort of multi-decadal swings in the temperature patterns there. And so you can define this by several different indices. The one we're looking at here is the interdecadal Pacific oscillation. And we can argue about whether there are oscillations or whether it's more of just a pattern. Oscillation kind of implies that there's a strict time scale for it, like every 50 years or so. That might not be the case, especially when we look at our paleorecords. But we can certainly say it's a pattern and it lasts for several decades. And so it goes through these warm and cold phases that you can see here. So colder phase around, the 1870s, warmer around 1900, colder around the 50s and the 60s, and then warm again, and then colder today. And so we were thinking, okay, well, how would an El Nino look in 1982, 1983, in the middle of this warm phase, 97, 98, still kind of in the middle of that warm phase, versus the one that just occurred in 2015, 2016 in this colder phase of this multi-decadal variability. So we wanted to get a better understanding of this multi-decadal variability. And it's been done before. There are lots of reconstructions of this type of variability. And they don't agree very well at all. So this is a composite of these different indices or reconstructions of the specific multi-decadal variability. And if you did an average of each century, whether it's kind of a more warmer or more of a colder phase, for each of these indices, you get variable answers. So for the 20th century, we can see, okay, 6 of those reconstructions tell us the 20th century was more of a positive phase, but 3 of them say, well, it was probably more negative. And it's, it equals out pretty much looking at these different centuries. So there's not a lot of agreement. And so we thought this was coming kind of from the regional biases in these reconstructions. So most of them focus on one region. If there's tree rings from, let's say, Northwest North America, or tree rings from Southeast Asia, or from the Southwest US, or coral records from, the equatorial Pacific. They're just focusing on that one region. And so what we wanted to do was broaden out. We've got this global collection of ice cores. Maybe we can select a few of those to get a bigger picture of what's happening in the Pacific. So this is the assemblage of ice cores that we used. We were looking at the Dasupu core from the Himalaya, the Bona-Churchill ice core from Alaska, the Quelccaya core from southern Peru, and then the Bruce Plateau core from the Antarctic Peninsula. And so this is the pattern of the positive interdecadal Pacific oscillation. You can see that in the sea surface temperatures, so that it really looks kind of like an El Nino, but essentially that warm equatorial tongue. And then you've got kind of the tripole of the colder areas above, north of that and south of that. And then the sea level pressure anomalies are in the contours, the black contours there. And so you can see how these different sort of semi-permanent pressure areas also differ during various IPO stages. And so it has an influence on all of these sites. So we wanted to put those records together to try to reconstruct the IPO back in time. And so this is what we came up with. And this was work that we published just this past year, earlier this year. And so what you see is our reconstruction in red versus the observations in black. And we can zoom in on the period, the observational period, back to 1850. And so we capture the variability really well. So, whether it's going to be kind of a colder phase or warmer phase, colder phase, but we don't capture the amplitude as well. So that's something we're still kind of looking into. We think it's probably due to a lot of the post-depositional effects with the ice core. So things like melting, diffusion, even just wind scouring can cause a lot of headaches for interpreting these ice cores. So it could be something like that. It could be the fact that, each of these sites, although they do respond to changes in the Pacific, it might not necessarily be dominated by changes in the Pacific. There are lots of local things going on as well. But either way, we've got a good capture of the variability, just not the amplitude. So the next step of this project is to try to tease out some of this multi-decadal Pacific influence. So focusing on those 4 sites again, if we understand what the background scenario is, are we able to understand what's happening with the monsoon? If we look at our Himalaya core, do we get a clearer picture of monsoon variability if we can kind of remove the influence, statistically remove the influence of the Pacific? Can we get a better impact or a better insight into what's happening with the North American ridge, the jet stream over North America? If we remove Pacific influence? Can we better identify individual ENSO events, El Nino events in our Quelccaya core if we can remove that background of the IPO? Can we distinguish between this, kind of canonical El Nino with that warm tongue, or the more central Pacific El Ninos, which seem to be becoming a bit more frequent these days? And then in Antarctica, can we get more insight on the Antarctic climate? Things like the southern annular mode. Maybe we can see a better picture of that in our Bruce Plateau core. The South Pacific Convergence Zone, which kind of runs right towards the Antarctic Peninsula. So that's the next step of this project, is sort of look at these cores individually and see if we can tease out that regional to local scale variability once we've identified and can classify what's going on in the Pacific. And then I'll just leave it probably with this one, so there's time for questions. But another project that I'm working on that's in review is exploring the Arctic and mid-latitude linkages over the past millennium. So again, kind of switching focus, not focusing on the equatorial Pacific, moving up towards the Arctic, but doing sort of the similar idea of looking at this assemblage of cores to try to understand these linkages between them. So focusing like on North America and the extreme events that we've been seeing here that are increasing, how does that relate to changes in the Arctic? That's kind of a controversial topic these days, where some think that the Arctic amplification and warming in the Arctic is amplifying our jet stream. But again, we just have this short observational record to look at. So maybe these cores can give us some insight over the last millennium of how the Arctic and the mid-latitudes might be linked in that way. So we want to compare our Alaska core with our Greenland cores. And then that's kind of the first sector. And then the second sector, comparing our Greenland cores all the way around to our Tibetan Plateau cores to see if we can understand things like Greenland blocking or Ural blocking. And then the third sector, kind of going from our Tibetan Plateau cores back to our Alaska core to see if we can understand changes in Eurasian snow cover, changes in the Siberian high, the Aleutian low, and how all of that sort of connects in the large scale. So that's the idea for the next project. And I've got maybe a couple more slides, but I might just end it there so that there's plenty of time for questions.
Thank you. I feel like I have a lot of questions. That was really, really interesting and really well presented. Thank you. So let's see, we are going to open it up to questions. Again, I see that a couple ended up in the chat. Please put new questions into the Q&A and we have one that came up earlier in your talk that is from a postdoctoral researcher here at Carey, Dr. Z. Grabowski. If you disambiguate black carbon soot from wildfires versus fossil fuel combustion, can you do that? How are you able to do that? And if you do, is it relevant in the time period that you're looking at?
Yeah, so the way I would say I don't know that there's a really way to separate the anthropogenic impact versus kind of the natural wildfire, but we're kind of just assuming based on the time period that we're looking at. So currently one of my colleagues has a paper in review focusing on Alaska and the black carbon there. And so we're looking at, years prior to when, there were lots of anthropogenic emissions. And so we can kind of safely assume that it was it was natural. But when we focus on the more recent parts of the record, yeah, separating those out is difficult. But we do see sort of an increase in that anthropogenic input as well. And we can compare that with some of the kind of modeled black carbon in that area and some of the emission estimates from that area. But yeah, how you separate it in the core, there could be ways. That's that's for the chemists in our groups to figure out.
When you, in the decadal analyses and questions, I'm curious, what limits your resolution there? What do you think is most limiting? Is it, so I'm trying to even envision like how much ice is that you're, that represents a decade or multi-decade as you go back in time, and is there enough to kind of get the patterns you're looking for? Anyway, what limits your resolution as you think about time?
Yeah, so for the time period that we focused on, which is really kind of the second half of the last millennium, we have annual resolution in our cores. So we can see things on a year-to-year basis, and we've made sure we've got several samples per year. So we have annual resolution, but we're just focusing more on the longer time scales, primarily because there could be time scale errors in our cores. So, we might think this layer is, 1856, but it's really 1857. And if you're looking at individual like El Niño events, that's going to, cause a huge hiccup. So we focused more on the long-term variability, kind of that, multi-decadal time scale, because then you're smoothing it out. You're not worried about whether you're off a year or so. And that's our estimate of our time scale error. It gets worse when you go further down in the core, but for the time period we're focused on, we're thinking it's probably just about a year or so that we could be off at any given point. But otherwise, yeah, the resolution is really good. So we're fortunate that ICE can provide us that annual resolution. I would love if we could see, seasonal resolution, especially with things like El Niños, which typically, are more common in the kind of northern hemisphere winters. But that gets a little dicier. And it depends too on the accumulation rates at the different sites. Some of our sites have a lot of accumulation, so you've got a lot of ice to work with, lots of samples per year, and some, not quite as much.
Okay, so when you say not quite as much, are you talking about like centimeters or even less for a given like 10 years of ice?
Oh, for 10 years of, oh yeah. No, we'd still have far more than that. Now the layers do get compressed the further down you go, just from the weight of the ice on top. But the resolution that we measure at is about a centimeter, and we still have several samples in a given year. So yeah, over a decade, we feel pretty confident.
It's really impressive. So we have a question from Dr. Winslow Hansen, who's a scientist here at Carey. I think you showed the PDO in a negative or cold phase despite rapidly warming mean climate in Alaska. Can we predict what the consequences for climate in Alaska will be if the PDO switch to a positive in conjunction with anthropogenic climate trends?
Yeah, so I mean, you would anticipate that it would be, amplified under current warming scenarios, but there's so many moving pieces that it's hard to just tie, what's happening to Alaska to the Pacific, because I think, like my other project, which hopefully gets funded, I think we see a lot of influence from the Arctic warming, and that's having a big influence on that ridge structure and that kind of jet stream pattern, which is causing that, really extreme warming in Alaska. But yeah, you would anticipate that in conjunction with a positive PDO and more El Niño events, that it would amplify even further. I mean, that would be my best guess to it.
I'm trying to think of how to word this. What do you think, what would you say is the biggest kind of unknown in trying to use the ice core data to predict into the future? What, is it?
Well, there's always that kind of stationarity issue. And that's coming with every sort of paleo record. You build your relationships on what we observe today, and then you just kind of extrapolate that back into the past. But does that relationship hold, especially when we know that, for pretty much all of our observational records, we've been altering the climate. So there's that external factor that isn't at play, deeper in the core. But we just sort of have to assume that, the relationships we see today hold in the past as well. So I think that's one of kind of the biggest mysteries, and the biggest thing we have to figure out is stationarity, and how you do that. I'm not sure. I don't have the best answers for that. But it's one of the assumptions that we just have to make in the paleo world, that you're just sort of like, oh, just hold your breath and hope.
Well, and so oftentimes the uncertainties get translated into kind of forecast uncertainty that has one meaning in the science and another meaning in media or in public recipients. My understanding is that the temperature expectations are pretty well constrained going forward, right? The forecast of how temperature will change is pretty well constrained. What do you think is the most open-ended forecast goal? Is it drought? Is it something? Is there a certain region?
So I think at least one of the things that I've heard the most is, and this is going to be a very oversimplification, but the wet places get wetter, the dry places get drier. And how those temperature differences manifest in different regions, how they affect the hydrologic cycle in different regions. I think it's that sort of a regional scale that we struggle with the most in our predictions, but it's getting better. I know with, the IPCC and all of those, intermodal comparison groups, that they're focusing on that regional aspect as well, to try to make those predictions better. But I think that's where, we know the globe will continue to warm, but how that impacts, Eastern North America versus Western North America, how that affects Western Europe versus Eurasia. I think that's where there's still some uncertainty.
Mm-hmm. It's all really interesting. And so I'm not seeing new questions at the moment. So I think we're going to let you go and have a bit of a lunch break so that a subset of us will gather again at 1 to talk a little bit more in depth. But thank you so much for your talk, and thank you to the audience for joining us today. Again, we look forward to seeing you on December 9th, right? Not next week, obviously. And unfortunately, because it will be a holiday here in the US, and not the week after because we had an unfortunate cancellation, but the following week. So with that, thank you all. And Dr. Porter, we'll see you on Zoom in about an hour.
All right. Thank you for having me.